Planes in three-dimensional space. To describe a plane, we need any three non-collinear points that happen to be in the plane. But is there a different way, perhaps a better way, to describe a plane? And my claim is that there is one way we do often in multivariable calculus, which is, what if we had a point that's in a plane, and then I have a vector which is going to be normal to the plane. Now consider any vector that is normal but that's in the plane. So this vector here, which I'm going to call v, imagine that is in my plane. Now that vector v could be shorter, longer, and in fact it could be all of these different vectors, etc. Now, take this vector v and all the different ones of all the different lengths and rotate it 360 degrees around this point. Can you see how this would form a plane? So if this will form a plane, how can we use this to find the equation of a plane in three-dimensional space? So let's consider the drawing now. We have a point, P naught, which is x naught, y naught, z naught, which is our fixed point. And then we have a vector which we will determine, or we will assume for now, that is going to be normal to our plane. We have another point in the plane, P, x, y, z, which is a random point, which really represents all the other points of the plane. Now recall that we could describe a point in space using a vector that starts at the origin. So P naught could be described using the vector R naught. And the random point P, meaning all the other points, can be described using the vector R. Then we get some following results. We can see that R minus R naught is going to be the vector x minus x naught, y minus y naught, and z minus z naught. And let's define our normal vector as a, b, c. We know, since n is perpendicular or normal to the vector r minus r naught, that the dot product of these two, and I'll put r minus r naught first, must equal 0, right? Because the dot product is related to the cosine of the angle. And if the dot product equals 0, then the cosine of the angle 0 means that the angle is 90 degrees. So if we fill in, that is, substitute our r minus r naught and our n, and then do the dot product, we see that a times x minus x naught plus b times y minus y naught plus c times z minus z naught must equal 0. And if we write this out and do a different substitution, or I'll redefine something in a second, we get ax plus by plus cz plus d equals 0, where d is going to be the negative of ax naught plus by naught plus c z naught. But this is the equation of a plane in three-dimensional space that we will often use. So let me do just a few problems with this. Suppose that the equation of a plane is given by 4x minus 3y plus 2z equals -5. And let's find a vector normal to this plane. This is a pretty straightforward problem because my equation ax plus by plus cz plus d equals 0, I just happen to move the d over to the other side, which isn't going to matter. In that equation, we know and we define the normal vector to be a, b, c. So in this example, our normal vector, or a normal vector, would be 4, comma, -3, comma 2. And we're done. Let's do a problem that's a little bit more involved. Let's find an equation of a plane that passes through 3 points. And let's call the point P, and that'll be the point 1, 3, 2. And we have a Q, which is the point 3, -1, 6. And the point R, which is 5, 2, 0. Now, how can we find an equation that passes through these 3 points? Well, we could do a system of equations. Perhaps ax plus by plus cz equals -d or plus d equals 0. Maybe that'll work. Do we have enough information? Doesn't really matter because we're going to do it a different way. Let's find the vector PQ to start. So PQ is going to be the vector 2, -4, 4. And let's also find the vector PR, which would be the vector 4, -1, -2. Convince yourself that we have these correct. And notice that both vectors are in the plane. If P, Q, and R are in the plane, the vector PQ and the vector PR are also in the plane. So let's do the let's do the cross product of PQ and PR. I, J, K, and then 2, -4, 4. I could have reduced this if I wanted to. And then 4, -1, -2. And we'll do the cross product of this. So we're going to get I, then times 8 minus -4. And then minus J times -4 minus 16. And then plus K times -2 minus -16. And let's double check this really quick. 8 plus 4, -4 minus 16, and then -2 plus 16. So we get 12i and then plus 20j plus 14k. We could simplify this if we wanted to. We could use 6i plus 10j plus 7k. Now, why do we care about this? How does this help us? Well, recall that the cross product of two vectors is perpendicular to both vectors. So what we've done is we've found our normal vector, which is 6, 10, 7. Now we need any point in the plane. I'm going to use the point P, and we can write the equation of the plane, which is going to be 6 times x minus 1 plus 10 times y minus 3 plus 7 times z minus 2 equals 0. Now, where do I get this from, just in case you're wondering? I'll call P, I'll make that P naught, just for the sake of this part. And then our random point will be the point x, y, z. And so we get the vector, what we call r minus r naught above, is going to be the vector x minus 1, comma y minus 3, comma z minus 2. And then we want to dot product that with our vector n. And I put the n first. And notice how we get exactly what I wrote here. Then if we write that all out, and I'll let you do the algebra, the mathematics, really the arithmetic behind it, we get 6x plus 10y plus 7z equals 50. Or minus 50 equals 0. And this will be the equation of the plane that goes to those 3 points, or any multiple thereof. Let's look at one more example. Suppose we have two planes that may or may not intersect, and we want to find the angle between the two planes, where the first plane is x plus y plus z equals 1, and the second plane will be x minus 2y plus 3z equals 1. Now, how can we find the angle between the two planes? Well, let's start by finding the normal vector to both of these planes. So the normal to the first plane is 1, 1, 1. And the normal vector to the second plane is the vector 1, negative 2, 3. So instead of finding the angle between the planes, we can find the angle between the normal vectors, and we'll get the exact same answer. So how do we find the angle between two vectors? Well, we know that the cosine of theta is the dot product over the magnitudes. So doing the dot product up top, we get 1 minus 2 plus 3 all over the square root of 3 times the square root of 14, which gives us 2 over the square root of 42. And then using a calculator, we get theta is, I said equals, but approximately 72 degrees.